So, um, exam 2, covering sections, so it's a 4.1, and then 4.3 to 4.7 is on Wednesday. So we'll review on this Wednesday during the first, half hour, 40 minutes of class time, and then we'll start the exam. Make sure that everyone has your webcams working, so we can turn them on during the exam. Contact CTL if you're having trouble. Okay, I'm not going to, I want to make sure everybody has it. I'm not going to let anyone take the exam who doesn't have their webcam working. All right, so do that tomorrow. Contact the the Center for Teaching and Learning if you're having trouble getting it going. All right. So we need to finish up our discussion of section 4.7, the problems there. So last time we covered, how far did we get last time? Up to problem 318. So next will be problem 322. So section 4.7, number 322. 1 second, guys. I apologize. So 322. For the following exercises, use the second derivative test to classify any critical points and determine whether each critical point is maximum, minimum, saddle point, or none. So 322, we have 8xy times x plus y plus 7. Okay, so find the critical points. So the points at which the first partial derivatives are both 0. So I think I'm going to multiply this through plus 8x.
I think your mic is muted.
Oh, is my mic muted? Okay. You can hear me now? Do I have this recording moving? I do. All right. So the function 8x squared y plus 8xy squared plus 7. We're going to find the critical points first and then determine whether that critical point is a relative maximum, relative minimum, or neither. So, partial derivative with respect to x, 16xy plus 8y squared. We're going to set that to be 0. And then partial derivative with respect to y, 8x squared plus 16y, xy. And set that equal to 0. So, these are symmetric functions, so we can expect, the symmetry with x and y, so we can expect that the critical points are going to have equal x and y coordinates or something like that. All right, so we can solve for x in the first equation. So 16xy equals 8y squared, dividing by 16y, and we have just y over 2, yeah? So x is equal to y over 2, and then using x equal y over 2 in this equation, we see what we get. So 8y over 2 squared plus 16y over 2 times y. So these are both 8y squared.
Would the x be negative?
Oh, negative, yes. So x is negative y over 2. So negative y over 2, and then that's going to be a negative. So 8y squared. Yeah, so not quite. So this is 8 over 4, 2y squared minus 8y squared. So just giving me equals 0. Giving us minus 6y squared equals 0. So of course just y is equal to 0. So y is equal to 0, and then x is going to be equal to 0 again. So xy equal to 0, 0 is the only critical point. Right, I mean, we could do this process in reverse over here, setting, solving for y in terms of x, and then putting it over here, and then, it'll give us the same thing. So, going now to the second derivative test. Well, what does the second derivative test tell us, right? The second derivative test is, to check this 2 by 2 determinant D, which is fxx, fxy, fyx, fyy, all at 0, 0. Well, x and y are both equal to 0, right? So when I take the second derivative here, what's fxx going to be? Fxx is going to be 16y. Fyy is going to be 16x. And then fxy is going to be, so here's fx, derivative with respect to y, is 16x plus 16y. Plugging in x and y equal to 0 and 0 just gives me 0, 0, 0, 0, which gives that, 2 by 2 determinant equal to 0. So the second derivative test is inconclusive. So, hence showing the limitations of what that test can tell you. The next problem in the list here (324). So same problem, this time with this function, x to the third plus y to the third minus 300x minus 75y. So same directions. fxy equal to x to the third plus y to the third. Minus 300x minus 75y. Minus 3. Minus 3. So partial derivatives are partial derivative with respect to x, 3x squared minus 300. And the rest of these terms are just 0. So you set that equal to 0, so you have x squared equal to 100. So x is plus or minus 10. And then fy, 3y squared minus 75 is 0. So y squared is equal to, so 75 is 25. So y is equal to plus or minus 5. So we get 4 critical points. So at all 4 of these points, both first partial derivatives are 0. So there are the critical points 10, 5, 10 minus 5, minus 10, 5, and minus 10 minus 5. Looking at the second partial derivatives, so fxx is going to be 6x, and fxy is going to be 0, and then fyy is going to be 6y. So that 2 by 2 determinant, at xy, so not at any one of the specific 4 points just yet, is fxx, fxy, fyx, fyy. So we have 6x, 6y, 0, and 0. So 36xy. Okay, so at the various points, what do we get? So at 10, 5, d10, 5 is positive, right? And fxx at 10, 5 is equal to, what is it? 60, which again is positive, right? So what does that tell you in these situations, if you remember? Right, when the d is positive, where is it? It's in here somewhere. When the d is positive and fxx is positive, it's a local max. Right, the d has to be positive to tell you local max or local min. And then, when it's a local max or local min, it's told by the second derivative of f. Okay, so the d being positive and the second derivative with respect to x of f is positive means that it's local max or min, and it's concave up at that point. Concave up in the x direction, right, because it's positive here, would give you a local minimum. Concave down, local maximum, right? And then when d is negative, a saddle point, and d equal to 0, inconclusive, right? So I think we're going to get all the possibilities here, right? So this is a local minimum at minus 10, 5. Well, we're going to have d less than 0, right? So that's a saddle point. At 10 minus 5, well, again, the d is going to be less than 0, so saddle point. And at minus 10 minus 5, right, the d, which is 36xy, so 36 times 50, is again positive. But this time, fxx at minus 10 minus 5 is going to be equal to, so what was fx? 6. So minus 60, so that's less than 0. So this is a local max. All right, so this is a nice function. It gives you, some variety, 4 different critical points, and all the different possibilities: a local minimum, local maximum, and 2 saddle points. Don't think I'm necessarily going to test you on this usage of this 2x2 determinant. What more so I want to have you tested on would be, well, let's see, there's 333 and 339. Are those any different? 333, 339. Well, 339 might be interesting. Why don't we take a look at that one? But what about 333? I mean, just look at it and tell me what it is. Where's critical point and what is... Oh, no, that's not a squared. I thought that was a squared. X squared plus y squared plus, yeah, it's x squared plus y squared plus 2x. Well, still... Well, let's give that one a look. Let's take a look at 333. All right, so find critical points. Determine if they are local max, mins, or saddle points. Or you can't tell. So fxy is equal to, so e to the minus x squared plus y squared plus 2x. Okay, so the partial derivative with respect to x, well, e to this thing, x squared plus y squared plus 2x, times the derivative of the inside, 2x plus 2, setting that equal to 0. And that just tells us what? X equal to... Right, the e is never 0, right? E is never 0, so this just tells us that 2x plus 2 is equal to 0. So x is minus 1. Partial derivative with respect to y, e to the minus x squared plus y squared plus 2x times the derivative of the inside, 2y. Setting that equal to 0, well, again, the e is never 0, so we just have that y is equal to 0. So minus 1, 0 is the only critical point. And what's it going to be? I mean, geometrically, this is an exponential function, right? Right, e to the negative of, this quantity up here. So, I mean, what does this surface look like? So, I mean, if we had a surface that looked like that, if you complete the square, this is x squared plus 2x plus 1 plus 2 plus y squared, and then minus 1. So this is x plus 1 squared plus y squared minus 1 is equal to z. So that is the paraboloid, right? Which has its minimum point for this one at 0, -1, or -1, 0. Right? So that's the paraboloid at -1, 0. So at that point, it's a minimum, and after that, the paraboloid just goes up, right? I mean, a paraboloid bottoms out at one point, and then it goes up after that. So for this function, it's going to be a relative max, right? And paraboloid look like this. So that's -1, 0, and then the z coordinate is going to be 0 or -1 at that point. Right, so that's what this surface is. So when you take e to that power, you're going to have a relative, because it's going to e to that negative power, it's going to give you a relative maximum at that point. Right, and then after that, the exponent is just going to get larger and larger, which is going to make e to that negative quantity smaller and smaller. But I mean, let's check it out. Let's check it out and see. All right, so -1, 0 will be a relative maximum for e to the minus x squared plus y squared plus 2x. Well, I mean, we don't have to stick it into this d. I mean, we see that that's going to be the case. Should we take the time to do it? Let's not, actually. Let's not take the time to do that, because I mean, we know what the answer is going to be, just from the knowledge of how the exponential function works, and the fact that we know what the shape of the paraboloid is. We know that that's going to be a relative maximum. Taking the second derivative, there's going to be some, some algebra there. That's maybe going to be a little bit much, is there? Well, let's check it out. fxx. So we have to use the product rule. So the derivative of the e, so that's e to the minus x squared plus y squared plus 2x. Oh, there's supposed to be a negative here, actually. And there's also supposed to be a negative here. So that negative goes away, and here we'll get 2x plus 2 squared plus the derivative of the 2x plus 2, which is just 2, times that. So there's going to be a minus there. So this is e to the minus x squared plus y squared plus 2x times, so this is 2x plus 2, quantity squared, minus 2. So that's e to the minus, that expression. So that's 4x squared plus 4x plus 4. No, plus 8x plus 4 minus 2 plus 2. And then fyy So here's the derivative with respect to y, taking the derivative with respect to y again. So I'm going to have e to that quantity times 2y again, so 4y squared, minus e to this quantity, 2y times the 2x plus 2. So that's e to the minus this expression, and we've got 4y squared minus 4xy plus 4y. And then fxy so this is just a constant, so it's going to be 2y times the 2x plus 2 times this. So e to the minus this expression, 2x plus 2 times 2y. Oh, this is a 2y. I'm taking the derivative with respect to y. This is just a 2 here. So 4y squared minus 2. And then this one is e to the minus, and then 4xy plus 4y. All right, so at minus 1, 0. So fxx at minus 1, 0. So this is what? So e. Well, it's going to be 0, right? At minus 1, 0. It's going to be where that paraboloid bottoms out. So it's 1. Or not 0, but negative 1 up here. So that's 1 plus 0 minus 1, or minus 2, so it gives you minus 1. So minus e, so it's e to the minus 1. So e to the minus 1, which is a positive quantity. And then plugging in the minus 1 into this, 4 minus 8 plus 2 is minus 2. So this is a negative quantity. All right, so it's minus 2 over e, which is negative. fyy at minus 1, 0. Right, so already, now we're, this is a negative quantity. We know it's going to be a relative max, geometrically. We're just confirming that with the calculations here. The fyy at minus 1, 0. So this is e to the minus 1 again. And then this is going to be negative 2. So minus 2 over e again. And then the fxy at minus 1, 0. So this is 0, 0. So it's just 0. Right? This is e to the negative 1 again. But right here, both terms have a y in it, so that's just 0. So the d at minus 1, 0 is the 2 by 2 determinant, minus 2 over e, minus 2 over e, 0, 0. So that's 4 over e squared, which is positive, right? So the d is positive. The second derivative, fxx, is negative. So minus 1, 0 is a local max, right? Um, 339. I'll leave that for you to do on your own because I want to move on to these problems here. So I don't think I'm going to test you on that 2 by 2 determinant. What's more interesting are these types of problems here, like 346. So find the absolute maximum and minimum values of, here it is, find the absolute extrema of the given function on the indicated closed and bounded set, right? So when you have, remember, so find absolute max and min for f, x, y equal to x to the third minus 3xy, xy, plus, was it? Minus y to the third, on the region defined by, so that's the square defined by x going from minus 2 to 2 and y going from minus 2 to 2. Right, so that's the x-axis, y-axis, 2, 2, minus 2, 2, or 2 minus 2, minus 2, 2, and minus 2, minus 2. So when you have a continuous function on a closed and bounded interval or region like this, the absolute maximum and minimum occurs either at a critical point inside or on the boundary. But on the boundary, the two-variable function reduces to a one-variable function. And finding the maximum and minimum of a one-variable function on a bounded interval, that's from Calc 1, right? So step 1 would be to find the critical points in the interior of this region. Okay, so first, find critical points in the interior and check the value of f, x, y at those points. So you don't have to determine whether that point is a relative maximum or a relative minimum. I mean, if you're going to have a maximum or minimum at, those points, critical points at the interior, they're going to have to be a local maximum or minimum. But, determining the difference between local maximum, minimum, and saddle point is unnecessary. right? Because you can only have finitely many points to check. Well, ideally, you might have more, but ideally you should only have finitely many points to check here. All right, so let's take partial derivatives. So we have 3x squared minus 3y equals 0. And fy is equal to minus 3x minus 3y squared equals 0. Right, so two equations, two unknowns. We can solve for y here. So this equation says y is equal to x squared. Putting that over here, we have minus 3x minus x to the fourth is 0. So x to the fourth minus x is 0. Y is equal to x squared, right? So this is x times x to the third minus 1 is 0. So this tells us that x is equal to 0, or what? What are the solutions to this here? X is equal to 0, or x is equal to... When is x to the third equal to 1?
When x is 1.
Just when x is 1, that's it. Right, the roots of the equation x to the n equals 1, the roots to that equation are complex numbers. I don't know if anyone's covered that with you yet in any of the math classes that you've had. But the roots to this are in the complex plane. Like this is the real axis and this is the imaginary axis. And the roots are like evenly spaced points on that circle. And the only real values you get are 1 and minus 1. So over here, they're complex numbers. Right? They're n distinct roots that are all complex or imaginary numbers. Right? But the only real solutions you ever get to x to n equal to 1 are 1 and negative 1. Okay? So, by the way, that's, a really nice reason for using complex numbers is because the number of solutions to this is n, as it should be. Shouldn't have missing solutions. There's n of them, and they're equally spaced points, along the unit circle in the complex plane. But anyway, again, the only real solutions you ever get are 1 and negative 1. But negative 1, not necessarily. That's only when you have n is even. So in this equation, negative 1 to the third, of course, is not equal to 1. So you always get 1 as a solution. And if you have like x to the fourth equal to 1, then you get negative 1 as well. So x is equal to 0 and x is equal to 1. So now we got to find the corresponding y values. Right? When x is equal to 0, y is equal to 0. Right, y is equal to x squared is equal to 0 also. So you have critical point 0, 0. And then when x is equal to 1, y is equal to x squared is equal to 1. So we have critical point 1, 1. So two critical points there. Now just check their values. So f of 0, 0 is, well, it's 0, right? Was there a constant? No. F of 0, 0 is 0, and f of 1 is 1 minus 3 minus 1. Is minus 2. So far we've got 2 points tested. And we have a value of f of 0 at 0, 0 and negative 2 at 1, 1. Okay, now we need to check the boundary. Of R. Okay, and the boundary is this square. So the square here consists of 4 sides. All right, so this is 2, 2, and this is 2, minus 2. Minus 2, minus 2, and this is minus 2, 2. So let's characterize these sides. What do the coordinates of this side look like? What are the coordinates of this side? The top one here. Well, the y-coordinate is always 2, right? And the x-coordinate is x. So here the coordinates are x, comma 2. So again, the two-variable function will turn into a one-variable function, where simply we're just going to plug in y equal to 2 and get some function for x. So here the points are x, comma 2, and x goes from minus 2 to 2. Down here, the points are x, comma negative 2, where x is again going from minus 2 to 2. And then the vertical sides, this is 2 comma y, minus 2 less than or equal to y less than or equal to 2. And this side is minus 2y, minus 2 less than or equal to y less than or equal to 2. So we have these four sides to check, but the function should, simplify quite a bit here. So let's copy the function. And let's look at the four sides. Okay, top side. So put that function there for reference. So on the top side, x is x and y is 2. Right? So the function becomes, and we'll just call it f. And it's going to turn into a one-variable function. So that's x to the third minus 6x minus 8. X to the third minus 6x minus 8. Again, for minus 2 less than or equal to x less than or equal to 2. So that's a single variable function. A single variable function on a bounded interval. How do you find the absolute maximum and minimum of the single variable function on the bounded interval? From Calc 1, how did you do that? Do you remember, guys? From Calc 1?
That the first derivative does.
Yeah, check the first derivative. Right, you find the, so I mean, again, the same language. You find the critical points, and that's where the derivative, and here we're just talking ordinary single variable derivative, 3x squared minus 6, where that's equal to 0, or it's undefined. So this is x squared equal to 2. So x is equal to plus or minus the square root of 2. So we have 2 critical points and 2 endpoints. So you check all of those. Right? So f at 2. Okay, well actually why don't we call it g of x, because it's a function for x. So we'll just call it g this time around. So g of 2, what's g of 2 equal to? So it's 8 minus 12 minus 8, so 8 minus 20 minus 16. So I mean already we've beat out these 2 points, 0 and negative 2. And then g of negative 2 is equal to, so that's minus 8 plus 12 minus 8. So minus 16 plus 12 is minus 4. then g of square root 2. So that is 2 root 2 minus 6 root 2 minus 8. So minus 4 root 2 minus 8. So we need to know approximately what that is. And, well, I don't think it's not gonna beat out this. It's not gonna beat out the minus 16. So it's negative, well, so 1.41 times 4 plus 8. So 13.64. So not quite the minus 16. And then g of the positive or negative square root 2 is going to be equal to negative 2 root 2 plus 6 root 2 minus 8. So this is positive 4 root 2 minus 8 minus 8, and that one's 2.36. Negative 2.36. All right, so we've got all these values here. So you remember that's how we find the absolute maximum minimum of the single variable function on the bounded interval, right? But we're not just comparing this function, we're comparing the function on all four sides with the value of the functions in the interior. And so far we've got 0 and negative 2. 0, negative 2 in the interior, and then minus 16 and all these various other numbers. So far the max is 0, the min is minus 16. So that's for the top. For the bottom, this is g of x, and you're just plugging in y equal to negative 2. So that's going to be x to the third plus 6x plus 8. Again, minus 2 less than or equal to x less than or equal to. By the way, when we check the top and the bottom, we check the corners as well. We checked this corner, this corner, this corner, and this corner, so we don't have to check them again. So taking the first derivative, so it's 3x squared plus 6 equals 0. So no solutions, right? So no solutions. But we do have to check the endpoints. So g of 2, so that's going to be the max, obviously. 8 plus 12 plus 8, so that's 28. And g of negative 2 minus 8 minus 12 plus 8, so it's minus 20. Minus 20 plus 8 is minus 12. All right, so we did top, bottom. Now let's do left and right. So the left is x is equal to minus 2. So we're going to have a function of y this time. So the x is minus 2, so that's minus 8 plus 3y minus y to the third minus 2 less than y less than 2. We don't have to worry about the 2 and negative 2, because when we checked 2 and negative 2 along the top, we checked these points already, right? So, and then on the bottom we checked this corner and this corner. So we didn't need to check them again. We just need to check the interior here. So g prime of y is equal to, make sure I got that right. So minus 8 plus 6y minus y to the third. 6y. Minus 8 plus 6y minus y to the third. So the derivative is 6 minus 3y squared. Set that equal to 0. So y is equal to plus or minus square root 2. So checking these values, g of square root 2, I imagine it's going to be pretty much the same, isn't it? G of square root 2, so it's minus 8 plus 4 root 2. So that's, yeah, or this one, minus 2.36. And then g of negative root 2, so that's minus 8, minus 6, minus 2, minus 8 root 2. Same number. Oh, minus 8 root 2. Did I have that wrong this time? No. X to the third minus 8. So that was positive here. So that's 2 root 2 minus 6 root 2. Also, this is the minimum here. So 1.41 times 8 plus 8. So, yeah, minus 19.28. So that's a long one. I mean, because the boundary of the stupid region is a square with 4 sides. It'd be easier if we had a circle or triangle or something like that, something with just one component. Okay, so the max is 0. Maximum is 0. And the minimum, we had nothing bigger than 0. Oh no, 28. So the absolute max is 28. All right, and the absolute min is minus 19.28. Okay, so that was a long problem. Let's look at another one of these. This is the kind of problem I like to ask on an exam, although not quite this nasty. What number was that we just did? 346. $347. Let's look at 347. So we're going to do one problem like on the exam, like 344 to 347. Okay, so one problem. On exam 2, like 344 through 347. So let's try 347. So here we've got fxy equals minus 2y over x squared plus y squared plus 1. Find the absolute max and min on the region R equal to, so this is what? X squared plus y squared less than or equal to 4. Right, so what's that? X squared plus y squared less than or equal to 4. All right, that's the circle of radius 2 in the xy plane. Okay, so we're just looking at, now this one is going to be much easier. Please pay attention to this. This one's going to be a lot easier because the boundary is essentially just given by one equation. X squared plus y squared equal to 4. All right, so on the boundary, as x squared plus y squared equal to 4. So we'll do that later. So first we'll find the critical points in the interior. So first, find critical points in the interior of R. All right, so find the first partial derivatives. So the partial derivative with respect to x, so this is just a constant on the top. So it's 2y x squared plus y squared plus 1 to the negative 2 times 2x. So this is equal to 2xy over x squared plus y squared plus 1 quantity squared. Setting that equal to 0, well, the bottom is never 0, so it's just 2xy equals 0. So this means x is 0 or y is 0. So, that's not telling us too much just yet. And now the partial derivative with respect to y. So derivative of the top is minus 2 times the bottom. Minus the derivative of the bottom, which is 2y, times the top, minus 2y, all over the bottom squared. Setting that equal to 0. So this gives us, so what do we have here? So 4y squared minus 2y squared. So that's 2y squared minus 2x squared minus 2, yeah? Minus 2x squared minus 2y squared minus 2 plus 4y squared over x squared plus y squared plus 1 squared equals 0. Right, so either x is equal to 0 or y is equal to 0. Now the bottom, of course, is never 0, so we're just looking at y squared minus x squared equals minus 2 equals 0, or minus 1 equals 0. Right, the bottom is never equal to 0, so I don't have to worry about that here. So if x is equal to 0, then y squared minus 1 is 0. So y is equal to plus or minus, right? So y squared is equal to 1. So this is y is equal to plus 1 or minus 1. Right, so we have two critical points here, 0, 1, and 0, minus 1. If y is equal to 0, right, then you're going to have minus x squared minus 1 equals 0, right, so no solution. Right, so these are the only critical points. Right, so these are the critical points. And they're both in, by the way, they're both in the region, right? They're both inside of R. They are, I mean, it could be that your region misses them. Right? They're right there and there. So that's the critical points on the inside. I mean, maybe I picked like this is the region, or sort of like just the top half of the circle is the region. Like maybe we were just doing the top half of the circle, in which case just one of those points is inside the region. Okay, but not the case here, right? Just you have 2 points and they're both inside the region we're looking at. So now just test the function, right? So f of 0, 1, so x is 0, y is 1, and you get minus 2 over 2. So minus 1. And f of 0 minus 1 is positive 2 over 2, right? Positive 2 over 2, so positive 1. Right, so we have two values so far. Now check the boundary. The boundary of the region is x squared plus y squared equals 4. Right, so what is the function? The function is right here. Right, so fxy. Now, which variable should, so the two variable function on the boundary is going to become a one variable function. So we're going to eliminate one of the variables. Which one should we eliminate? Which variable should we eliminate, the x or the y? Which one should we try to eliminate? Which one will give us less trouble, essentially? You can do either or. Okay, but which one will give us less trouble?
Y?
Well, if we try to eliminate the y, we're going to have to use x is equal to plus or minus the square root of 4 minus y squared, right? Or sorry, if we try to eliminate the y, then y is going to be equal to plus or minus the square root of 4 minus y squared. So that goes here, right? So we would have to use it. So actually the function will become two functions. The function along the top half of the circle and the function along the bottom half of the circle, represented by the two, the positive square root and the negative square root. So, that we would like to avoid. If we eliminate the x, all we got to eliminate is x squared. So using x equal to 4 minus y squared, we get fxy becomes g of y equal to minus 2y over 4 minus y squared plus y squared plus 1. Yes, I mean, it just minus 2/3 y, just y, right? For what values of y? What are the values of y that we're using here on that region? What's the range for y? Or what's the domain for y in this region?
Between -2 and 2.
Yeah, between -2 and 2.
And then also, wouldn't x become the square root of 4 minus y squared?
Right, but there's no x.
No, it's saying using x equals 4 minus y squared.
Yeah, x is the x squared is, x squared is 4 minus y squared, right. We only have to use the x squared as 4 minus y squared because there's no x to fuss with here. Right, so again, this is, for the y is minus 2 to 2. For the x is minus 2 to 2. Right, so, well, there's no critical points. So g prime of y is never 0. Right, it's a line, so there's no critical points. So, so all you got to do is check the endpoints. So g of -2 is equal to 4/3, and g of 2 is -4/3. So what's the max and the min? So that's the max and the min, 4/3 and -4/3, right? So the absolute max is 4/3, and the absolute min is minus 4/3. So 1 1/3 and -1 1/3. Beats out the 1 and -1 at the critical points. Okay, so we'll have one problem like that on the exam tomorrow. Finding this absolute max and min of a two-variable function on this bounded region. Okay, again, the idea is to find the critical points on the inside of the region by taking the first partial derivative with respect to x, first partial derivative with respect to y, setting them equal to 0 and solving simultaneously, getting a couple critical points. Check which critical points are actually inside of that, right? And then test it. Plug those critical points into your function and, see what you get. -1 and 1. Right? And then check the boundary. And on the boundary, I'm not going to give you a square. I'm going to give you a hexagon so you have 6 sides to check, right? So on the boundary, you're going to have different components. Luckily, with the circle, there's only one component. And, you have to check each component, each segment, or something, split up the boundary in some way that makes sense. And then the 2-variable function becomes a 1-variable function, because the curve that you're checking in the xy plane, you can write y as a function of x or x as a function of y somehow. All right. Let's see, are there any more of those that are worth taking a look at? So we did 346, 347. 345 again is on a circle. 344 is on a triangular region. Let's try 344. Let's do 344 as well. So for 344, we have fxy is xy minus x minus 3y. All right, so find absolute max and min on region R equal to 0, 0, 0, 4, 5, 0. So we've got 0, 0, 0, 4, and 5, 0. All right, so we've got this right triangle region. So now the boundary is going to have, 3 components. And let's right at the beginning here, let's take a look and see what we can do with these components. So how do we express the points along the bottom here? How do we express the points along the bottom here? All right, well, the x is just x, and the y coordinate is
0.
0, right? With range of, or domain for x, 0 less than or equal to x less than or equal to 5. On this vertical side, we've got x is 0, y 0 less than or equal to y less than or equal to 4. And then along the slant here, well, what's this line? Let's just write it. Y is mx plus b. So slope, rise over run, minus 4/5 x plus 4, 0 less than or equal to x less than or equal to 5. Right, so along the slant here, you have y is minus 5x plus 4, 0 less than or equal to x less than or equal to 5. So we'll eliminate the y in that case, and it's no big deal because the function's pretty simple, whichever one you eliminate. All right, so we've already expressed the boundary here. By the way, when you check in the boundary, there's only 3 corners to this thing. So with x, you're checking x from 0 to 5. You only have to check the 0 once. So you can do it along the bottom and the 5 once along the bottom. And then along the top, along the left side, vertical side, you only have to check that endpoint because you'll have already checked that one. And then along the slant, you won't have to check any of the endpoints because you'll already have done them if you check the sides in that order. Bottom, left side, and then the slant. Okay, so critical points in the interior. So partial derivative with respect to x. So y minus 1. This is easy. All right, so y is 1. F of y or f, partial derivative of f with respect to y, x minus 3 is 0, so x is 3. So 3, 1 is the only critical point. All right, and that is inside this, right? So 3, 1 is like right about there. That's the only critical point in the interior. So just plug it into the function, check it out. You don't have to check that determinant to see what, what if it's a relative max or min or whatever it is. I mean, there's only finitely many points to check here, so ideally. So 3, 1, so this is 3 times 1 is 3, minus 3, minus 3, so it's minus 3. All right, so at the critical point, or yeah, at the one critical point in the interior, you have fxy equal to minus 3. Now let's check the boundary. So along the bottom, right, fxy becomes g of x, y is 0, so it's just minus x. Right, so it's linear. So now you just check the endpoints. So g of 0 is 0, and g of 5 is minus 5. So along the vertical side, x is 0, so you just get g of y equal to minus 3y. So again, you just got to check the boundaries from 0 to 4. You don't have to check g of 0 in this one because that corresponds to that point. You've already checked it right here. So we just have to check g of 4. So that's minus 12. And then on the slant, you've got y is minus 4/5 x plus 4. So g of x is equal to x minus 4/5 x plus 4. Let's take this down below. So that's x times y minus x minus 3y. Or 3y is minus 4/5 x plus 4. All right, so this one's a little bit more entertaining here. So minus 4/5 x squared plus 4x minus x plus 12/5 x minus 12. Right, so 4x minus, so 3x over 5, so it's 15x over 5. So 15, so it's 27x over 5. Minus 4/5 x squared minus 27 over 5, or plus 27 over 5x minus 12. Right, so that's my single variable function obtained from the two variable function along that slant. Right, along that slant we use that y is equal to minus 4/5 x plus 4. Let me double check that. Squared, so 4x minus x is 3x. So 3 plus 12 over 27 over 5. Okay. So now that function is not a line; it's a parabola. So we have to check the derivative. So g prime of x is minus 8/5 x plus 27 over 5, setting that equal to 0. So 27 over 8 is equal to x. Right, 27/5 equals 8/5 x. So it's 27 over 8. So that's 3 and a bit. 3 and a third or something. Okay, so plugging in this point into the g, so g of 27 over 8 is going to be equal to, well, pull out the Wolfram alpha, I think. from? So minus 4/5 times 27/8 squared plus 27/5 times 27/8 minus 12. So minus 2.88. Right, so there we have it. So we have a relative maximum of 0 and a relative minimum of minus 12, or absolute maximum. Absolute max is 0 and absolute min is minus 12. Okay. Is there any question about these three problems we just did? Right. You check the now checking the boundary is the lengthy part of doing this. Finding these critical points on the inside and then plugging those critical points into the function that goes a little bit more quickly. Checking the boundary, tends to be a little bit more tedious in this type of problem. But again, that goes back to Calc 1, because you're just taking the two variable function, transforming it into a single variable function, and then you're finding maximum and minimum of that single variable function. So you find the maximum and minimum of the single variable function on on each side, and then you compare those maximums and minimums to the maximum and minimum from the interior points, right? And by the way, make sure you don't do any double checking on the boundary. I mean, we check both boundary points on the bottom, right? So we don't have to check the bottom boundary point on the side here, just the top one. And then on the slant, we already checked the left and the right end point of the slant, so we didn't, when we did the bottom and the vertical, so we didn't have to check them again. We just checked the interior point on the slant. Questions on that? On that procedure? It's involved. It takes. You got to stick with it. I'll try to make a problem where the boundary is easy to deal with. Last few problems in this section. So, in Calc 1, there was this problem on applied max. There was this whole section, right, on applied maximum and minimum problems. It's not in this book. This is just the multivariable book. Right, and there was all these like geometric type problems. Well, in all of those problems in Calc 1, essentially you had to boil down all the information they give you into a single variable function. And you take the derivative of that single variable function, and you find the maximum or absolute max or absolute min of that single variable function. But with the multivariable calculus, I mean, depending on how many variables you're using, you can find these maximums and minimums, for a wider variety of problems. Although the single variable stuff is really quite interesting. There's a lot of beautiful geometric problems in those. So let's take a look at one of the ones they have here. We got 346. We did that. 349. So find the points on the surface x squared minus yz equal to 5 that's closest to the origin. So points on that surface closest to the origin. So 349. So on the surface, what was it? X squared minus yz equal to 5. Find the points x, y, z that are closest to the origin, right? 0, 0, 0. Well, on the surface, so we can boil this down to a two-variable function because we're talking about this surface here. So x squared minus yz equal to 5. So this becomes x squared minus 5 equals yz. So z is equal to x squared minus 5 over y. Right? So the distance of x, y, x squared minus 5 over y from 0, 0, 0, right, is given by the distance formula. So that's x minus 0 squared plus y minus 0 squared plus z minus 0 squared, like that. Right, to minimize the distance, since the distance is a square root, we just minimize the thing on the inside. Right, to minimize distance d, which is the square root of this, just minimize the interior, but the function under the square root. All right, so that function is fxy equal to x squared plus y squared plus x squared minus 5 over y, that whole thing squared. All right, is there any implied interval for x and y? Is there any region implied for x and y? I mean, on this surface. Well, aside from avoiding y equal to 0, right? I mean, aside from avoiding y equal to 0, except if you're just talking about the point 0, 0, 0, or I guess 0, x equal to 0, y equal to 0, z equal to whatever. You know, aside from just avoiding that, you know, there's no restrictions on x and y in this function here, right? Just, you know, for this function, we just have to avoid y equal to 0. But here you can have y equal to 0. If you have y equal to 0, oh, then x, z could be any, well, y equal to 0 is a special case, apparently. Okay, but aside from the y equal to 0, there's no restrictions, so the minimum must occur at a critical point. You know, or at a point where y is equal to 0, right? Because the surface is defined when y is equal to 0, right? You've got x equal to plus and minus the root 5, and z can be anything. So in particular, z could be 0. But, we'll look at those later. So the minimum of this function must occur at a critical point. So the partial derivatives with respect to x here, this is 2x plus 0 plus this one is 2x squared minus 5 over y to the first power times the derivative of the inside, 2x over y. Setting that equal to 0. So this is 2x plus maybe we should, well, this will be fine. So 4x times x squared minus 5 over y squared equals 0. Multiply both sides by y squared. Well, this is a bit much now, isn't it? I mean, that is really quite... Maybe we should write it as x equal to the square root of 5 minus yz. I think that is going to be a better way to do it, because this is just going to be too difficult here. So this is going to be x squared equals 5 plus yz. So x would be equal to plus or minus the square root of 5 plus yz. Right, and then this point becomes, so x is plus or minus square root 5 plus yz, and then you're having y and z as the independent variables. So the distance from 0, 0, 0, 0, 0 to that point is going to be, so plus or minus the square root 5 plus yz minus 0 squared plus y minus 0 squared plus z minus 0 squared. So to minimize the square root, you just minimize the function underneath the square root. So the function is in terms of y and z, but it just becomes, in this case, and then we don't even have to worry about the plus or minus business. It just becomes 5y plus z plus y squared plus z squared. So the minimum must occur at a critical point, or at a point where, well, actually we don't even have to worry about this anymore. Even that's gone. So the minimum must occur at a critical point. Let me just get rid of this stuff here. So partial derivative of f with respect to y is 5 plus 2y, setting that equal to 0. So y is minus 2/5 and minus 5/2. And f of z is equal, partial derivative of f with respect to z is just 1 plus 2z, setting that equal to 0, so z is equal to negative 1/2. So that's it right there. Right? So the smallest distance from the origin on that surface is, well, the y is minus 5/2. The z is negative 1/2. And the x is square root 5 plus yz. Well, plus or minus that square root. So 5 plus yz. Oops, wait, what did I do? 5 plus, I have 5 plus yz. I put 5y plus z. So this is wrong. So partial derivative of f with respect to y, z plus 2y is equal to 0. So y is equal to minus z over 2. And then partial derivative with respect to z is y plus 2z equal to 0. And then using y as minus z over 2. So that's z times 2 minus 1/2. So that's 3/2. Z is equal to 0. So y is equal to z is equal to 0. Right? So the closest point is, or the closest points are occur at these critical points, or at this critical point. So you have x, y, z equal to, now x is 5 plus 0 square root. So x is the square root of 5 or negative the square root of 5. All right, so is that an odd numbered problem? Yeah, 349, so you can check that in the back. There it is. Root 500 and negative root 500. Takes you long enough to load up. Gosh. What else? Applied maximum minimum problems. So 353, 355. Oh, we don't have. So 352. Let's look at 352. Going back to this sort of classical problem from Calc 1. So in 352, we've got a cardboard box without a lid is to be made with a volume of 4 cubic feet. Find the dimensions of the box that require the least amount of cardboard. Okay, so 352. So cardboard box without a top is made has 4 foot cubed volume. So find dimensions. Which use the least amount of cardboard. So you've got this box, and there's no lid on it, and we'll say the width is X, the depth is Y, and the height is Z. So, yeah, 4 feet cubed. So you have that X times Y times Z is 4. But we're trying to minimize the amount of cardboard used. Right? So minimize, so the surface area, which is the amount of cardboard used. So the surface area is equal to what? Well, it's xy for the bottom, plus 2yz for the left and right, plus 2xz for the front and the back. So you want to minimize A subject to the constraint x, y, z equals 4. So what you can do is you can use the constraint to reduce the number of variables, right? We know how to deal with finding maximums and minimums with 2 variable functions. So, reducing this to a 2 variable function using that constraint is helpful for us. So in this constraint, we've got x times y times z is 4, so z is equal to 4 over xy. So this is xy plus 2y times 4 over xy plus 2x times 4 over xy. So the surface area is xy plus 8 over x plus 8 over y. Right, so we want to minimize A subject to this constraint, so we're minimizing this function. Now, is there any well-defined boundaries for x and y? Are there any, special boundaries for x and y? Like, x has got to be at least 1 and y is, at most 10 or something like that. Is there any boundary on just x by itself, or any boundary on y just by itself? Well, the answer is no. I mean, the only constraint really is that x and y have to both be positive, right? But they can be as long as you'd like or as short as you'd like, as long as they're positive. So other than x and y being bigger than or equal to 0, the minimum must occur at the critical points. At one of the critical points, if there's going to be more than one. Typically these things only have one. So the minimum value for A, X, Y must occur at a critical point, of which probably there's only one, but we'll find out. Right, so the partial derivative of A with respect to X is Y minus 8 over x squared equal to 0. So this tells us that, y is equal to 8 over x squared. And then partial derivative of a with respect to y is x minus 8 over y squared. So setting that equal to 0 and plugging in this, so we have a minus, or x minus 8 over x squared is 0. So we have x minus x to the 4th over 8 is 0. Multiply both sides by 8, I guess. We encountered this one already, didn't we? That's neat. So factor out x. Or no, it's different. It was 1 here before. 8 minus x to the 3rd is 0. So this says that x is equal to 0, or x to the 3rd equals 8. So that's x is the cube root of 8. So x is equal to 0. Well, of course, x can't be 0, right? So x has got to be the cube root of 8. And, this is all, these partial derivatives are symmetric with regard to x and y. So y is, is going to be cube root of 8 again, right? I mean, 8 over the cube root of 8 squared leaves, the cube root of 8. So, and then y is equal to 8 over x squared, which is going to be the cube root of 8 again. So the critical point is x equal to the cube root of 8, y equal to the cube root of 8, and then z is equal to what? 4 over the cube root of 8 squared. Come on. Right, and the minimum must occur here. So the dimensions are x equal to the 3rd root of 8, y equal to the 3rd root of 8, z equal to 4 over 8 to the 2/3. So what is that? I don't know. 4. Eight to the right. Cube root of 8 is 2 squared. 4 is 1. Z is equal to 1, right? Of course. Is equal to 1. So this is the dimensions which minimize the surface area. So the amount of cardboard used. Now, back in Calc 1, you would have done a similar problem. I mean, that's a really standard sort of example that you get in Calc 1. Find the dimensions of a box with a certain volume that minimizes the surface area. The only problem is in Calc 1, what do they add in with the box problem that we didn't do here? There was one constraint on the box in the Calc 1 problem that we didn't have here. And we didn't have to have that constraint because, we're dealing with we can deal with 2 variable functions now. Finding maximums and minimums. Anyone remember what that constraint was on the box in Calc 1? The bottom had to be what?
Was it a square, so you only dealt with 2 variables?
Right, exactly. right? So the bottom of the box had to be a square. So the width on the bottom, so the area on the bottom was x squared, right? So this was x, and this was x, and that was the height h or something like that. Of course, the minimum occurs when it is a square on the bottom, but you don't assume that right from the get-go, right? I mean, it had to turn out to be that way because the function that you're dealing with to minimize, right, is symmetric in regard to x and y. So it can't be that you get an ace. Well, I guess it could be. Well, I mean, it's not a surprise that the minimum occurs when you have a square, right? Right. So those are the applied max and min problems. I'd like to leave it at that for those. So what kind of questions would you, at this point, like, let's start our review of chapter 4. So we can start with whatever section that you guys want, but what questions would you guys have, or what points would you like cleared up about chapter 4? So anything 4.1, 4.3 up to 4.7. We didn't really cover 4.2 directly, and we're not covering 4.8, although 4.8 is pretty interesting.
Could you go over vertical traces?
The level curves, you mean? The contour?
Well, contour maps, yeah, that
Yeah,
too.
yeah. So where did we do that? Was it in 4.1 or was it in 4.3? I guess it was in 4.1, huh? So in 4.1, on level curves. Find the level curves of each function, the indicated values of c to visualize the given function. So, for example, let's see, what's a nice one? Okay, so let's say like 25. So 25, so 4.1, number 25. So fxy is equal to xy minus x. So they want to see level curves for c, or f equal to -2, 0, and 2. So draw level curves for f equal to -2, 0, and 2. Okay, so, well, at 0. So 0 equal to xy minus x. So if you factor out the x, right, you have x times y minus 1. So this means x is equal to 0 or y is equal to 1. So the level curve for f equal to 0, or z equal to 0 maybe we should call it z, is, well, x equal to 0. So x equal to 0, that's the y-axis, yeah? Or y equal to 1. And that would be this line right here. So this is the level curve for z equal to 0. The y-axis and this line. This is the x-axis and the y-axis here. I don't like the fact that it's on the y-axis itself, but that's what it's got here. Let's try 2 and negative 2. So at 2 equal to z, we've got 2 is equal to x times y minus 1. So different ways we can look at this. Right? Y is equal to 2 over x plus 1. Right? So y equal to 2 over x, right? That's this curve here. And we're adding 1 to it, so it goes above this line here. Right, so this, so this is z equal to 0, z equal to 0. So now this one is z equal to 2. And then z equal to negative 2. So minus 2 over x plus 1 equals y. So that's the curve down over here. And it's equal to 0, I guess. Where does it cross the x-axis? So at x equal to negative 2. Alright, so that's the 3 level curves for this function. And then the level curves for other values of z, for larger positive values of z, will be over here. And for larger negative values of z, will be over here, like that. And that's it. It's just, drawing some of these level curves. The level curves together give you this thing called the contour map. What was special about the contour map with regard to the gradient, say? Do you remember what was special about the contour map and the gradient? The level curves and the gradient function, the gradient vectors. You guys remember? The gradient and the level curves are always what? They were always what? They were always perpendicular. Right? The gradient function in this case is so y minus 1 x and at any point that you choose, whichever level curve that you land on, the gradient vector is going to be perpendicular. So at this point here, at negative 2, 0, we get what? So at negative 2, 0, you get negative 1, negative 2. All right, so that's the gradient the vector. Negative 1, negative 2. At that one point there. The gradient is always perpendicular to the level curves. Okay, that was always an important point. And wherever else you're going to pick it, So, for example, if you pick it here at, say, x equal or y equal to 1, at y equal to 1, you get 0, 0x, right? So here's the gradient function here at 0, 1, or yeah, at 1, 1. So at 1, 1, you get the gradient is 0, 1. And over here, say, at like -5, 0, the gradient is going to be, well, it's going to be really long. 0 minus 5 is equal to the gradient. And as you can see, pointing straight down is perpendicular to the horizontal line. Or right over here, right, the x is equal to 0, and the y is equal to, something minus 1. So the gradient points this way, in this case, down here. All right, so like at y equal to -4 there, or something like that. So that's like -5, 0. The gradient is always perpendicular to the level curves. What else? What else would you guys like to discuss? What else, guys, from chapter 4?
Could you go over the linear approximation problems?
Yeah, let's take a look at that. So, tangent planes, linear approximations. So, where are they? So 195. So z is equal to x e to the y. Compute delta z from P12 to Q1.05, 2.1, and then approximate the change in z using the differential dz. And then, compare that. dz and delta z are actually close to each other. Okay, so fxy is x e to the y. So what number is this? This is 195 in section 4.4. This was in section 4.1, yeah. So calculate change in z from 1. There we go. 1.2 to 1.05 to 2.1. So calculate the actual change in z and the differential linear approximation change in z dz from 1.2 or from 1 comma 2 to 1.05 2.1. Okay, so first of all, okay, let's find those partial derivatives. The partial derivative of f with respect to x, well, the e to the y is just constant, so it's e to the y. And the partial derivative with respect to y is just x is a constant times e to the y. So f, partial derivative of f with respect to x at 1 comma 2 is e squared. And the partial derivative of f with respect to y at 1 comma 2 is equal to e squared again. Okay, now the differential dz is equal to dx times the change in x plus dy times the change in y. The change in x is 0.05. Right, 1.05 minus 1, 0.05, and delta y is just 0.1, both positive. So the linear approximation change in z is e squared times 0.05 plus e squared times times 0.1. So that's equal to e squared times 0.15, which is approximately equal to what? So e squared times 0.15. So 1.1083. So the change in z along the tangent plane, or the differential change, is 1.1083. The actual change in z, delta z, is, well, it's f of 1, 2 minus f of 1 point, oops, other way around, sorry. F of 1.05 2.1 minus f of 1, 2. So that's 1.05 to times e to the 2.1 minus e squared. So 1.05 times e to the 2.1 minus e squared. $1.1854. Right, so about 8/100ths off from each other. Right, so these are fairly close. right? So that's the change in z of the function compared to the change in z along the tangent plane. Now, the actual value of like f of 1.05, 2.1, is e squared plus this differential, or plus the delta z. So that's just comparing the change. That's not actually estimating the actual value of the function. So for next time, let's compare this to number. So we did 198, I guess. I don't think we did 199. Well, no, again, that's just the change. Where are the problems where you actually estimate the function itself, or don't they actually have that in here? Oh, they don't actually do that in this book. Find the total differential. Yeah, they actually don't do that in here. That's fine. So for next, we just won't do it. So for next time, we'll try 199. So try 199 on your own. And we'll look at this next time as well if you've got questions. Okay, so for next time, we'll review for the first half hour, 40 minutes. Okay, so come with any last minute questions. If you want to meet with me, guys, send me an email and we can find a few minutes to meet at some point. All right, on Collaborate also, or on WebEx or something of that sort. Alrighty, so have a good night, and I'll see you on Wednesday.
Thank you.